My name is Joey Werbel, and this is Lab 4, a mass and spring system in 2 dimensions. In this lab, our objective was to analyze the motion of a mass moving in elliptical orbit on the end of a spring. Then, using data from that motion, a computer model was constructed to represent similar motion. In order to do this, video of the motion was processed in Tracker. Using extracted data from the Tracker analysis, a model was then constructed in Python to represent the system. From here, the original motion and the model could be compared. The result was that the final product was a model that accurately represented the periodic motion of a mass moving elliptically on the end of a spring. Relevant equations for this lab were the energy principle, which states the total change in energy in a system must be zero, the equation for potential spring energy, which is potential equals 1/2 times the spring constant times the displacement squared, the gravitational potential energy, which is equal to mass times the gravitational constant times height, kinetic energy of an object, which is 1/2 times the mass of the object times the magnitude of the velocity squared, the force of gravity, which is negative mass times the gravitational constant, spring force, which is the negative spring constant times the displacement, and for this lab, total energy, which is the potential spring energy, potential gravitational energy, and kinetic energy. When analyzed in Tracker, it can be seen that the mass moves in an elliptical orbit, which is tracked in red here. This then gave an output of time values, x position values, and y position values, which we would use later in the Python model. Here we initialize the Python model. We set the mass equal to 0.402 kilograms, the initial position of the mass, which comes from the Tracker data, the initial velocity, which is 0 as it is released from rest, and the initial time, which is also 0. Set a time step small enough to give an accurate curve, the gravitational constant equal to 9.8, the spring constant, which we got from the lecture video, to be 6.89, the relaxed length of the spring, which is calculated to be 0.123 meters, and we calculated the length of the spring using the initial position of the ball and the initial length of the spring, as well as an L-hat vector for the spring. Next, we have our computation of force and energy in the system. We start with force using the 3 equations for kinetic, gravitational potential, and spring potential that we saw earlier. Then, we enter a loop where the gravitational force, the spring force, and F-net are calculated in order to update the position of the ball and the velocity of the ball. From here, we update the length of the spring and the L-hat associated with it. Finally, we calculate the change in energy during every loop. Here we see the change in kinetic energy, the change in gravitational potential, and the change in spring potential. When this code is run, we see mass moving in an elliptical orbit, the blue being the model and the red being the data from Tracker. You can see that they follow each other fairly closely, and we get a graph of all of the changes in energy over the course of the run. Now we can analyze the data from the model. Here we see that the red line is the change in potential spring energy, the blue line is the change in kinetic energy, the green line is the change in gravitational potential energy, and the yellow line is the total change in energy of the system. Note that the total change in energy of the system is just about 0. The first conclusion question is the energy principle satisfied? This was shown somewhat on the last slide, but to put it more bluntly, yes, or at least very close to being satisfied. The energy principle states that the change in total energy in a system will always be 0. The yellow line on the graph just seen shows that the change in total energy in this system is just about zero, with a slight wobble for the entire course of the motion. The second conclusion question asks us to compare the period of the motion, both calculated from an x position point of view and a y position point of view. Here we see that for two periods calculated from the x position, they're roughly the same. When we look at the period calculated from the y position, there's a noticeable difference, quite a decrease. Now, this difference is due to the fact that in the x position, the mass is moving as a pendulum, and in the y position, the mass is moving due to spring motion. The periods for these two types of motion are generally calculated using different formulas, and therefore will have slightly different values.